Welcome to the Explainer. Now, for all you focused learners out there, we're going to completely skip the usual agenda today. Why? Because we have this fascinating mechanical mystery to solve right now. It's all about rig hoisting systems, and honestly, it challenges literally everything you might assume about heavy lifting.
Okay, let's just dive straight into this. Imagine a 1¼ inch thick steel drilling line. Its absolute braking strength is right around 40 tons, but the weight of the drill string it needs to lift? Try 250 tons. By all logic, that really should be the end of the story, right? The rope should just snap. Except, oil rigs are out there lifting this massive weight every single day, using that exact same 40-ton rope. So, how on earth are we beating the math here?
Section 1. The crown block. The 2,000-year-old secret. The answer to this whole puzzle actually sits about 140 feet in the air. The crown block is basically this massive, heavy steel frame right at the very top of the derrick. It houses a row of grooved pulleys, which, out in the industry we call sheaves, and they're all arranged side by side on a common shaft. But here's the absolute most important thing to remember. It is completely fixed. The crown block itself never ever moves. Below it hangs the traveling block, which obviously does move up and down. The drilling line runs up to the crown, down to the traveling block, and then back up again, weaving these two blocks together into one giant cohesive system.
Section 2. Multiplying the line. Mechanical advantage.
So, how exactly does weaving a rope back and forth keep it from snapping? Well, it all comes down to mechanical advantage, specifically a process called reeving. You see, you haven't magically made that wire rope any stronger. Instead, you've taken this massively heavy job and divided it between multiple rope lengths instead of just one. Every single pass of the line between the fixed crown block up top and the moving traveling block below actually carries a share of the load. If you string 8 lines, each pass carries roughly 1/8 of the weight. String 12 lines, and each carries roughly 1/12. You've essentially taken an impossible weight and converted it into totally manageable fractions.
But, this naturally brings up a pretty interesting question for all the engineers out there. If 12 lines share the load 12 ways, why not just string 16 lines and get even more capacity? Take a brief second here. Think about what you might actually lose if you add more lines.
Did you figure it out? The cost of power is speed. More lines absolutely equal greater lifting power, for sure. But if you string 16 lines to raise that massive block just one single foot in the air, the Drawworks down on the floor has to spool in 16 feet of wire line. That makes lifting incredibly slow. And because tripping pipe in and out of the hole just consumes a massive amount of super expensive rig time, you don't just string as many lines as possible. The line count is a really deliberate job-by-job trade-off. Crews will string more lines for those heavy casing runs and then drop down to fewer lines when they need fast tripping.
Section 3. The hidden loads, anchors, and instruments. Now, the crown block really acts as the pivot for everything else in the hoisting system. Let's trace the actual path of that single continuous drilling line. One end of the rope runs all the way down to the Drawworks. We call that the fast line, basically because it moves fast, spooling in and out to do the heavy pulling. The completely opposite end of the rope runs down to the derrick floor and is firmly clamped to an anchor. We call that the dead line because it doesn't move at all. And right there, sitting on the dead line, is the weight indicator sensor. Because the tension is shared roughly equally across all those lines we were just talking about, everything the driller actually reads on their weight gauge is just tension measured right off that single, stationary dead line.
Now, what's really interesting here is the math of what the crown block is actually supporting. You might just assume it only carries the weight hanging on the hook, right? Well, think about it. The hook load pulls down. The fast line tension pulling from the Drawworks, that pulls down too. And the deadline tension at the anchor, yep, that also pulls down. So the total crown load is actually the hook load plus the fast line plus the deadline. That massive assembly sitting way up at the top of the derrick is always carrying significantly more weight than just what's hanging below it.
But of course, perfect physics really only exists on chalkboards. In the real world, we have to deal with this number, 81%. Every single time that thick wire rope bends around a sheave, you get friction. And because of that friction, 12 lines don't give you exactly 12 times the lifting capacity. A much more realistic efficiency figure for a standard 12-line string is right around 81%. You are always going to lose a little bit of capacity to the physical reality of the machine.
Section 4. When things break, wear and impact.
So, with hundreds of tons hanging in the air and friction constantly eating at the system, what actually happens when things go wrong? Well, there are two primary failure modes we need to talk about. First up is wear. Worn sheave grooves quietly pinch and cut the wire rope from the inside out exactly where you can't easily see it happening. That is exactly why sheaves have to be measured with precise gauges, not just eyeballed. The second mode is impact, or what the industry calls crowning out. If the driller hoists even a fraction too far, that moving traveling block slams right into the stationary crown block. It damages the whole assembly at once, parts the drilling line, and causes the traveling block to freefall 140 feet straight down to the rig floor. It is an absolutely catastrophic failure, which is why bumper blocks and safety limits are specifically installed to prevent it.
The really crucial point comes down to this idea. It's a block and tackle, the thing that lets one person pull an engine out of a car. You cannot make a wire rope that lifts 250 tons and still spools onto a drum, but you can reuse a modest rope 12 times. I absolutely love this. It just perfectly shows how identical physical principles scale up flawlessly from a totally relatable tool in your local garage right up to a multi-million-dollar rig. It isn't just about multiplying force. It's about taking an impossible materials problem and converting it into a brilliant, completely solvable mechanical one.
Which leaves us with this final thought for today. If a relatively fragile 40-ton rope can effortlessly lift 250 tons just by changing how it bends and loops through the air, what other impossible limits are we just blindly accepting in everyday engineering? Seriously, take a look around you today and ask yourself, where else are hidden mechanical advantages doing the impossible right in front of us? Thank you so much for joining me for this explainer, and definitely keep exploring the incredible mechanics of our world.